You are watching College Education Tutorial, your number one knowledge center where complex topics in engineering and mathematics are simplified. I'm Noah Adasi, and today we are breaking down volume of revolution. Come on, let's get started. So now imagine spinning a curve around an axis, like an x-axis or the y-axis. What you get is a 3D shape, that is a solid. And the volume of revolution is how we calculate the space inside the solid. We use integration to do this, and we can also think of slicing this solid into a very thin disc or shell and adding up their individual volumes to get the entire volume. And that's what we simply call volume of revolution. So now let's quickly move into the various methods of which we can calculate volume of revolution of a given curve. So now for the volume of revolution, we are going to talk about two main methods. That is the Dix method and the washer method. So basically, let's talk about the Dix method first. So for the Dix method, we use the Dix method when we are rotating a curve about the x-axis or the y-axis, and there is no gap between the curve that we are rotating and the axis of rotation. That is what you have to take note. And there is no gap between the curve that we are rotating and the axis of rotation. It has a formula v equal to pi integral of a to b f of x all squared dx. And we talk about this formula into details. But for now, the pi is a constant, as you know already, and then f of x is the function that you are revolving along the x-axis or the y-axis. So this is what I was trying to say over here. When we have a curve like this and we are trying to rotate it along this x-axis, we will get its corresponding curve like this. But don't forget that it is what? Symmetrical about the axis of rotation. So in that case, we will get a figure like this, which is a 3D shape. And for this figure, we can calculate what? The volume of this particular figure by using what? The Dix method. So let's quickly look at how this particular formula came about. So this formula came about by taking advantage of the area of the disc, which is what? The circular disc, right? The disc is a circular disc. And when we approximate something into a circular disc, then we can have its exact area, which is what? Pi r squared. So assuming we have a disc like this, then we can see that the area of this particular disc is what? Pi r squared. That is what? The area of this circular disc. So since we have the area for the disc as pi r squared, then we can say that the area is equal to pi r squared, where we will need the radius, which is r, of which we don't have it. So how do we find it from the curve that we have been given? So that's where you need to look at the graph of that particular function or the curve. So let's quickly look at something here. Also, if we have an area and we multiply another length, let's say the length is x, we multiply by the area, we get what? Volume. So in that case, when we do the integral introduces another x into the area function itself, so that when we multiply it, we get what? The volume. For instance, when you have integral of dx, it's the same as integral of 1 dx. Because it's 1, we don't write it. So in that case, when we are finding an integral of a constant, we get what? The variable that you are integrating with respect to. So if I'm finding the integral of 1 and I'm integrating it with respect to x, which is dx, therefore I'm going to get what? X plus a constant c. And if the constant is 0, then I can see that the integral of dx is what? X. So leveraging on this same approach, when I have the area and I integrate it, I introduce an extra x to multiply the area. In that case, I get what? A volume. Is that okay? So now if we are able to approximate that particular curve into an area of a circle, and therefore we find the integral of that particular figure or curve at that particular point, then we'll be able to approximate the volume at that point. and you know the integration of some of the individual volumes at each point, and in that case we will be able to get the entire volume of that particular figure. So let's quickly take a look at this example. So let's assume that we are approximating this at each point into a circular disc. At each point into a circular disc, you can see that we can find what the diameter of this disc, but we need what the radius. So how can we find the radius? And we can find the radius by taking one side of the figure, because remember this figure is what symmetrical about the axis of rotation. In this case is the x-axis. So what we can do is that from this point to that point here, from this point to that point here, and from this point to that point here is what is our radius. In that case, from our axis of rotation up to the function becomes what our radius at each point. And I'll use GeoGebra to show you how it look like. So that means that we can find the radius by looking at the distance from the axis of rotation to the function, and that one will give us what the corresponding what y value, and in that case we will be able to find what the radius of the circle at that particular point. So when you revolve it and you turn it into a 3D shape, you have to see something like this. And if we have something like this, you can see that from the axis of rotation, which is the x-axis here, to any parts of this function or this shape can be classified as what our radius, right? Can be classified as what our radius. So in that case, we have to find it mathematically. So in finding it mathematically, the only thing that we can do is that when you know the value of x here, we will have to just insert the value of x into the function, right, to give us its corresponding what y value. We know that the function will give us maybe y equal to a particular variable or expression, and in that case when I put in the x value to give me corresponding y value, and that becomes my radius at that point. So let's quickly look at GeoGebra how things were done. So looking at GeoGebra, as you can see on the screen over here, this is the function I'm talking about, right? The function here is y equal to x to the power 1 over 2. Let me get out the algebra panel. So as you can see, y equal to, or f of x equal to x to the power 1 over 2, and that is the function, and we are rotating it around this x-axis. Is that okay? Rotating around this x-axis. So since we are rotating around this x-axis, it means that at each point from this side up to this axis is going to be what our radius. So at this point is from here, let me put here. So at that point, at this point is from this point, at this point is from here to here will be our radius. At this point, when we are approximating to the circular disc, is from here to here to the curve will be our radius, and we can get its value by tracing it to what the y-axis. So in that case, I created this slider in such a way that you will be able to visualize it. So when I move this slider, you can see that at this point we will have what y value. At that point we have y value, at that point we have y value, and at this point we have y value, and at this point we have y value. So in that case, or at each point, it will be able to approximate the exact radius for this function. Let's really look at the full view of it. Let me go to graphic 2 so you can have a look at it. So now this is what you are seeing over here, right? This is what we are seeing. So for this, so if I am to approximate it into a circular at each point, you can see that I'll be able to calculate the radius at each point. So in that case, I'll have to put the x value over there at any point in time into the y function, and I'll be able to kind of find the distance from the axis here to that of the function, right? And that will be what my radius. right? But remember that this is actually what the full circle, and we just needed a radius, and the radius is from the axis of rotation to that for the function, and that's what you are seeing over there. So let's quickly go back and then look at other things. So now that we understand how we can get the radius from the curve, we can say that if the area of the circular disc is equal to pi r squared, then we also know that we can get our exact radius by putting in what the x value into the original function or the curve that we are rotating. So at x1 we will have to do f of what x1, and we will be able to get the radius at that point in the function. And then if at x2 we can also put it inside the function expression, and we will be able to get what the radius. So in that case we will say that at each point we'll be able to evaluate our radius, right? So in general, then we can say that the area of that particular hot figure, the disc that we approximated the curve into at that point, will be pi into bracket. Since our hot radius is f of x at each point in x, then we can say that our f of what x may be I, right, or squared, because the radius here is squared, right? So in that case, since we have our area, we can go ahead and then find the volume of what revolution. So how do we find the volume of revolution? So we find the volume of revolution for that figure by what? Integrating over the limits of like a to b of the area, right? And then with respect to the variable that we are working with. So in that case, we can say that the volume of revolution is equal to integral of the limit a to b pi into bracket f of what xi all what squared and then dx. And as I was saying earlier on, the integral sign or the integration kind of what introduce an extra x into our main function, and when we multiply by the area, we get the volume of revolution at that point. And one thing that it does is to kind of what add up the individual volume that it will calculate at each point in time to be able to accumulate or the entire volume of that particular figure, right? And that's how you will be able to kind of calculate the volume of revolution by using the Dix method. So in my next tutorial, I am going to talk about the washer method, and after talking about the washer method, then we will solve some examples later.